Hi everyone, Tina here, and today I'd like to talk about moments. You'll usually learn about this topic during year 2 of your A-level course. I'll go through some key ideas first and then we'll take a look at some examples. So here are some key ideas. First of all, the moment of a force measures the turning effect of the force on a rigid body. To calculate it, you say the moment about a point is equal to the force times the perpendicular distance to that point. So on this diagram here, we have the force times the perpendicular distance to that point. Another way of thinking about it is that the moment about point is actually equal to the perpendicular component of the force times the distance. And this is the version that I usually use in questions. So in this diagram, this would be the perpendicular component of the force F times that distance there. A lot of the time, rigid bodies will be in equilibrium, and when that happens, clockwise moments will be equal to anti-clockwise moments. So moments going this way will be equal to moments going that way. Let's take a look at some examples. Example 1. AB is a non-uniform rod of length 1 meter and weight 30 newtons. AB rests horizontally on supports placed at points C and D, with AC being 0.35 meters and DB being 0.25 meters, as shown in the diagram below. Given that the center of mass of AB is 0.45 meters from point A, calculate the reaction force at each of the support points. Now, because it's a non-uniform rod, that means its mass is not going to act at the center. We're told the center of mass of AB is 0.45 meters from point A. So I'll put that on the diagram first. 0.45 away from A, so that's an additional 0.1 meters here. We know the length of the rod is 1 meter in total, so that means this length here must be 0.3 meters. I'll then also label on the reaction forces, reaction at C, reaction at D, and that's what we're trying to find in this question. Now we have everything on the diagram, we're ready to answer the question. The rod is at rest, means it's in equilibrium. Therefore, we can say that forces up are going to be equal to forces down. Looking at the forces up, we have RC and RD, and then forces down, we just have 30. Because it's in equilibrium, we also know that clockwise moments are going to be equal to anti-clockwise moments. So if we take moments about C, I usually put a cross at the point that I'm taking moments about. Clockwise is going to be 30 times 0.1, and anti-clockwise is going to be RD times 0.4. If you solve this for RD, you get 7.5 newtons. Now, earlier we said that RC plus RD was equal to 30. To find RC, all we need to do is sub RD into that. Means RC is 22.5 newtons, and that's it. Example 2. A uniform rod AB has length 3 meters and mass 4 kilograms. The rod rests horizontally on two supports C and D, where AC is 0.5 meters and AD is 2 meters. Part A, find the magnitude of the reactions of the support at C and D. This time it's a uniform rod, length 3 meters, mass 4 kilograms. So we can put the weight of the rod in the center, maybe somewhere here, 4G. Because it's in the center, that's 1.5 meters on either side. We know this distance is 0.5 meters, which means this distance is going to be 1 meter. We know all the way from A to D is 2 meters, so 0.5 left here and 1 meter left there. We can put the reaction forces on, RC, RD, and that's everything on our diagram. Now we want the magnitude of the reactions again. So because the rod is at rest, we're in equilibrium. So once again, we can do forces up equals forces down. So we get RC plus RD equal to 4G. Equilibrium also means that clockwise moments equal anti-clockwise moments. So let's take moments about C, and I'm going to put a cross here. You could also take moments about D, by the way. It's just personal preference. If we do that, then clockwise we have 4G times 1, and anti-clockwise we have RD times 1.5. We solve for RD and we get 8 over 3G newtons. Find RC, we just sub into this equation. Very similar to the previous question. RC plus 8 over 3G equals 4G. That means RC is going to be 4 over 3G newtons. Part B. A block is now placed at B and the rod is on the point of tilting about D. Find the weight of the block. So now the scenario is changed, I'd probably draw a new diagram. So we've got the rod, A, B. It's still a uniform rod, so 4G is in the middle. We've still got the supports in the same place. They didn't say that those had moved. So we have reaction at C and reaction at D. I'd put the measurements on again. So 0.5 meters 1 meter, 0.5 meters, 1 meter. And then it says a block is placed at B. This block is going to have a weight, let's call it W, and that's what we want to find in this question. It says the rod is on the point of tilting, so not quite tilting yet, but it's on the point. That still means it's in equilibrium. So we can still use the fact that clockwise moments will equal anti-clockwise moments. Now with tilting, if it's on the point of tilting about D, what that means is that the reaction force at C is in fact going to be 0. Because if it's on the point of tilting about D, the rod is going to lift up from the support at C. Now in this case, I would specifically take moments about point D, because wherever you take moments about, you can ignore any forces at that point, and we don't really know what RD is. So that would give us W times 1 equals 4G times 0.5. RC is 0, so we don't need to count that in our moments. That means W equals 2G newtons. Now for part C, they want the magnitude of the reaction at D, so we want to find RD now. I would use forces up equal forces down here. Forces up are RC and RD. Forces down, we've got 4G plus the weight of the block. We know RC is 0, and we also know that the weight is 2G, so that means RD is going to be 6G newtons, and we're finished. Last example. In the following diagram, AB is a ladder of length 10 meters and mass 34 kilograms. End A of the ladder is resting against a smooth vertical wall, while end B rests on rough horizontal ground, so that the ladder makes an angle of 70 degrees with the ground, as shown below. The ladder is modelled as a uniform rod lying in a vertical plane perpendicular to the wall. The coefficient of friction between the ground and the ladder is mu. Given that the ladder is at rest in limiting equilibrium, calculate the value of mu. First thing I'm noticing is the fact that it's limiting equilibrium and friction is involved here. So I'm going to make a note that friction will be at its maximum, mu r. Then I'll go ahead and label the diagram. So it's a uniform rod. Uniform ladder means the weight will be in the middle, 34G, with 5 meters either side. There'll be a reaction at A, perpendicular to the wall. Let's call that RA. And there'll be a reaction at B, perpendicular to the floor. Let's call it RB. Friction is involved here, and that's what's holding the ladder in place. To work out which direction friction is acting in, think about what would happen if friction wasn't there. The ladder would slip. So friction must be acting in this direction to hold it in place. Now, the forces we have on the diagram are not perpendicular to the distances. So that's going to cause a problem when we're trying to do moments. So at this point, I would label on some angles and some components of the forces. We're going to want this component of the weight, and this angle here will also be 70 degrees. If that's a right angle, means this component will be 34G cos 70. This angle here will also be 70 because of alternate angles. So this component of RA will be RA sine 70. The ladder is at rest in equilibrium. So let's say forces up will equal forces down to begin with. I find that's always a good place to start. Forces up, RB, forces down, 34G. So that gives us that RB is equal to 34G straight away. We can also say that forces left are equal to forces right. Forces left, we just have friction, and forces right, we have the reaction force at A. Now we know friction is equal to mu r, so I'm going to replace friction with mu RB, because friction is acting on the floor at B. That's equal to RA. I'm going to sub in 34G for RB, so it's going to become 34G mu is equal to RA. Now in this question, we ultimately want to find mu. So if we can find RA, then we can calculate mu. Find RA, we're going to use moments. Let's take moments about point B. I'm choosing B because I want to work out what RA is, so that must be in the equation somewhere. Equilibrium, so clockwise equal anti-clockwise. Clockwise, we're going to have RA sine 70 times 10, the full length of the ladder. Anti-clockwise, we've got 34G cos 70 times 5. If you solve this for RA, you get 60.63744103 and more. You can then sub that value in to your equation from before to work out what mu is. So 34G mu is equal to this 60.63 number. Keep the full value in your calculator when you work out mu, and you'll get 0.18198, which is roughly 0.182 to 3 significant figures. That's it for now. If you found this video useful, please do remember to like, comment, and subscribe to my channel if you haven't already, and do share this with anyone else who you think might find it helpful. Thanks, and see you next time.